For our second talk this morning, we have Carla Cederbaum from Tübingen with the wonderful title, Coordinates RMSE. Carla.
Thanks a lot for the invitation, and let me announce that I'm on the second day back from maternity leave, and we may get an interruption from a hungry baby. I hope not. I tried my best to make the baby not hungry, but let's see. So coordinates are messy. I hope to convince you of this message in the course of the talk. So let me start by saying what setup I'm thinking of. So I'm thinking of a three-dimensional initial data set in general relativity, of course, where M3G is here Riemannian and K is a 0-2 smooth 0-2 tensor field on M3, playing the role of the second fundamental form or extrinsic curvature on the initial data set in the ambient spacetime, if you will. But most of what I'm going to say is purely working in the initial data set, and you can mostly forget about the spacetime around this initial data set for now. And I'm going to call such an initial data set AE for asymptotically Euclidean. If M3 can be split into a compact set in a disjoint union with something which is diffeomorphic to R3 minus above, where I'm going to call this diffeomorphism X. So these X consist of X1 and X2 and X3, which are then the asymptotic coordinates on the set M3, and then the components of the metric G with respect to these coordinate X. And I drop the push forward that's sitting here in my notation. It's implicit here, will be supposed to decay to the Euclidean Kronecker delta ij metric, plus terms of the order to the -1/2 minus epsilon, where epsilon is some positive quantity, r is the length of this X with respect to the Euclidean metric, and this goes to infinity. And of course, I'm asking something similar for the components of Ki with respect to the coordinates X, and that is the components decay like -3/2 minus epsilon. And in addition to this, I'm asking that both mu defined as the scalar curvature with respect to G minus K G squared plus trace with respect to G of K squared times 1/2, and also J equals the divergence G K minus trace G K times G are either in L1 or stronger than that. I will ask that they are O0 of R to the -3 minus 2 epsilon, where the epsilon is the same everywhere. And it's important to note that -3 minus 2 epsilon is not, and I stress this, is not what you get from taking derivatives of the metric components and the K, but it's an extra assumption which implies L1. So if you will, you can think of the L1 as the back way of saying that mu and J decay, and the O notation as a CK or Riemannian integrability sense of things. If you're not familiar with these little indices in my O's, let me briefly say what they mean. So the O0 is your usual O notation, and O1 or an O2 mean that correspondingly many derivatives of the objects that are in this O notation decay correspondingly. So the first derivative of something in O1 R -3 minus epsilon, -3/2 minus epsilon would be decaying like R -5/2 minus epsilon, which is exactly what the thing in the O does if you take a derivative. And if an O2 would say that I assume according decay for up to 2 derivatives. Okay, so this is just a shorthand notation. In this setting, we know from Bartnik in '86 that the well-known notion of ADM mass, ADM energy, ADM linear momentum, and ADM mass are well defined. Okay, So these are surface integral at infinity expressions in terms of for E first derivatives of the metric components. Here first 0th order terms in K, and M is the square root of PADM squared minus Euclidean length PADM squared. Okay, so we know this from Bartnik, and we'll talk a little bit more about the ingredients of this proof later when we need it. But for now, let me just assume that you're all familiar with these ADM quantities and that the fact that Bartnik proved that they find. You may have heard why I'm choosing this strange exponent here and not just write minus some decaying, minus some positive number. And the reason is very simple. If you do not assume that the xij is delta ij plus terms, and now I'm becoming sloppy with the number of derivatives because it doesn't matter for this example, r to the -1/2 minus epsilon, you are allowed, say, for the explicit example, gijx equals delta ij exactly, to choose asymptotic coordinates y as x times 1 plus some constant c over the square root of r. That's the r to the 1/2 there. And with respect to these coordinates, if you compute gijy, so these are the components of the metric with respect to these asymptotic coordinates derived through this formula from the x coordinates, where again, r is nothing else but the length of x, then this will be asymptotically Euclidean. Then this will be delta ij plus terms of the order r to the -1/2 without an epsilon and with infinitely many derivatives. But the ADM energy of this metric in these coordinates will be some expression proportional to c. In particular, if you don't choose this constant c in here 0, then the ADM energy in these coordinates will not be 0. Okay, so this is why you have to be better decaying in the metric than -1/2 minus epsilon. Then -1/2 have epsilon up here. And you can do similar things. And let me just add an example to Denisov and Soloviev in 83. Okay, so this is why we have to be decaying to the Euclidean metric better than 1/2. And do I need to decay for k better than -3/2? And there are multiple ways of answering this. One is constructing examples in similar spirits where then the ADM linear momentum will mess up. This is messy. Another way is that you want these conditions, these decay conditions, to be Poincare covariant. So if you take a space-time and you take a different slice in the same space-time, which arises from the first one by a continuous family, say a boost, then you want these conditions to be transforming equivariantly under these boosts, say, and these conditions are perfectly tailored to doing that, including the number of derivatives you ask in the indices of the O notation. Another question you may ask, and it's all going to be coming back later, is why do you have this, or alternatively this integrability condition on the energy density mu and the momentum density j of the initial data set? And I answer this first by an analogy to Newtonian gravity. where we are given a matter density rho. And then because it's a matter density, of course, the total Newtonian mass is going to be defined as the volume integral over that matter density. And of course, for this to be well defined, you will want integrability of this density. And so by analogy, it's not surprising that we will have to ask that mu and j, the relativistic energy and momentum densities, have to be integrable in order for something like energy, linear momentum, and mass to be well defined. So it's all very consistent. Of course, analogy, we also make these integrability assumptions on mu and j because they're needed in the proof by Bartnik in order to get that E, P, and M are well defined. Sweeping some steps under the rug here. For time's sake. So one thing I want to only, I don't want to sweep under the rug is that in Bartnik's proof, a very rough picture of what's going on is that, as I said, EADM is defined as a surface integral at infinity. And using a divergence theorem argument, you can roughly, and I write roughly here so nobody misunderstands me, as a volume integral plus an inner boundary term which is finite. And the volume integral is roughly over the energy density. And similar things work, of course, for PADM and the momentum density, as all of this is, of course, very well known, Bartnik's papers from the 80s. I just want to recall these facts because they're going to be important later in the new framework that, or in the framework I want to discuss. And so integrability of mu is relevant for convergence and finiteness of the ADM. Okay, so there's this analogy to the Newtonian setting, which becomes very apparent. Okay. So then I said already that the asymptotic Euclideanness conditions are Poincare covariant. And importantly for our talk, this means, for our topic today, this means that they're invariant in particular under Euclidean motions. What do I mean by that? By that I mean that if the AE conditions are satisfied on a given initial data set for some coordinates x, then we also hold y equals qx plus a, where this is a vector in R3 and this is a rotation matrix. Okay, so I can study different, as we already did in the example above, I can study different coordinate charts on the same initial data set, asymptotic coordinates x and asymptotic coordinates y, and if they differ by a Euclidean motion, then the asymptotic Euclideanness condition also hold for these y coordinates. But of course, this is very restrictive, and it's not the only type of coordinate change that I can perform that preserve the asymptotic Euclideanness conditions. For example, I can implicitly define coordinates y by is y plus the sine of the logarithm of s times a, where s is the absolute value of y. And if M3GK is asymptotically Euclidean with respect to the coordinates x, then it will also be asymptotically Euclidean with respect to the coordinates y. So AE for x, if and only if for y. So the class of asymptotic coordinate transformations that I can make is much richer than just Euclidean motions, but importantly, it contains Euclidean motions. An alternative example, and both of these examples will become relevant later, would be to define y implicitly as x equals y plus some function f of s times a, where again a is R3 and f is O3, sorry, 1 plus O3 of s to the minus alpha for some positive alpha. And I would call this an asymptotic translation. So if f was just the function 1, then of course this would be a translation. And so if f is asymptotic to 1 plus lower order terms, then it will be an asymptotic translation. So summarizing this introduction, everything, including the notion of asymptotically Euclidean coordinates. So all these coordinates that I've been discussing are asymptotically Euclidean coordinates, are clean and well understood. And also everything, as long as we only discuss energy, linear momentum, and mass, is very nicely analogous to the Newtonian gravity picture. So we have an analogy between the initial data set context and a time, a moment of time in Newtonian gravity. Of course, incorporating ideas from special relativity, where the matter densities here correspond to the matter density on this side. The ADM energy corresponds to the total mass, as we've seen in these brief, rough introduction to or view inside Bartnik's proof. And of course, sorry, this is a G and K correspond in some sense, which is very vague, to the Newtonian potential. Okay. So I can use this analogy, which I've already used to explain to you why it's plausible that mu and J should be integrable for EADM and PADM to be well defined. I can ahistorically mimic some funny coordinates in Newtonian gravity. So let me say what I mean. So this is very ahistoric, and probably no one would be crazy enough to do this, but it's very illustrative for what we're going to do. If I write Laplace U is 4 pi rho, now on R3, rho is the matter density, U is the Newtonian potential, then of course I can rewrite, just as I showed you in a nutshell for Bartnik's proof, the total mass as the volume integral, but then using the divergence theorem, I can write this as the normal derivative of the Newtonian potential integrated over a sphere at infinity. And this is the same sphere of the sphere at infinity in the relativity when you compute the ADM quantities. And of course I can do that, but now I can go back on my Euclidean space, which is a Euclidean space with respect to some Cartesian coordinates x. And I can define new coordinates y, because I'm a differential geometry, nobody stops me from doing so, implicitly by the same formula I showed you before, x is y plus sine of logarithm of s a, where a is a non-zero vector in R3, and s is the length of y. And then I can compute the components of the Euclidean metric with respect to these new coordinates y, and see that is, of course, asymptotically Euclidean for all epsilon positive, according to the definition above. That's something I've already told you in a different context. And then one can compute the total mass with respect to these coordinates y by the formula, by the surface integral formula here, and find that, of course, just as in the relativistic case, and this is very ahistorical because nobody would do this after the fact, but we can see that even in Newtonian gravity, you get this coordinate independence if you are happy to choose random asymptotically Euclidean coordinates on your Euclidean space. Okay, so I promised that coordinates will be messy. So far, coordinates haven't been very messy yet. Everything has been nice and giving the same results for energy, linear momentum, and mass. But let's go to where the mess begins and look at the center of mass. So look at the center of mass. And of course, you could also look at angular momentum and would have similar issues, but I'm just going to not mention that today altogether. And let's start for the center of mass in the Newtonian picture. The Newtonian picture tells you that the total center of mass is defined as 1 over the mass times the volume integral over rho times the position vector. This is the average position of a point in the matter density. And for this to be well defined, of course, I need this to be integrable. This will already inform us about integrability conditions we should expect in the Newtonian, in the relativistic case. And of course, I would need the total mass to be non-vanishing, as you would expect when you discuss a center of mass. And it's well known and easy to compute that if you translate or rotate your coordinates, so you perform Euclidean motions on your coordinate chart X, then the center of mass will transform accordingly. As one should expect. But if I'm freeing myself from the idea that I should work only in Cartesian coordinates, and I write y plus sine ln s a with a non-zero, and I compute this formula in terms of a surface integral formula, as I showed you for the mass, picking the simplest non-trivial potential I could choose, then the center of mass with respect to these y coordinates will diverge. Okay. Let me say this again. If I'm in Newtonian gravity and I pretend that I'm allowed to choose coordinates which make the Euclidean metric of Newtonian gravity asymptotically Euclidean, but that are not Cartesian coordinates, as you can see in the sine logarithm s term, then I can get my total center of mass to diverge in Newtonian gravity for a very, very reasonable Newtonian potential of an isolated point source of mass m. Okay. So in some sense, if I allow coordinates in Newtonian gravity, it gets messy. What do I draw from this? Let me highlight the things that we should take away for DR. If we are studying an initial data set, we should have some assumption that some quantity, and it will be the ADM energy, should be non-zero. We should have some assumption that some matter density times coordinate components should be integrable. We should expect some equivariant transformation under Euclidean motions of the coordinates. And we should expect that if the center of mass, whatever it's defined by, if it converges with respect to some coordinates x, then I can implicitly introduce these coordinates y, and it will diverge. Okay? And in GR, if I'm not in a setting where I have some symmetry, there are no Cartesian coordinates that give me any preferential treatment, as here in Newtonian gravity, where it seems absurd to transform coordinates this way. But in DR, if I have some coordinate chart x in which all this works perfectly well, then I transform to this coordinate chart y, then it will get messed up. Okay, so these are, and this is regardless of how the total center of mass will be defined in GR. This is something we should expect from Newtonian gravity already to happen. And we will see that this happens for all reasonable definitions of center of mass already on Riemannian Schwarzschild, which is the relativistic analog of this potential here. Okay. Also from special relativity, we should expect that k playing in some sense the role of an infinitesimal velocity or momentum of the initial data set in the space-time plays a role in the definition of center of mass in order for the center of mass to be able to transform equivariantly under the Poincare group. So expect K to appear in definition of C G R, and expect C to transform equivariantly under the Poincare group. So this is for any definition of center of mass that we would consider reasonable. We would expect these features and drawbacks from Newtonian gravity, and also these features from special relativity. And of course, these are all just ad hoc assumptions, but I hope I convinced you that they're well founded. Okay, so what are definitions of center of mass? And of course, I'm not going to talk about all of them. In particular, I'm not going to talk about the one by Mu-Tao Wang and Shengtung Yao and collaborators, Puning Chen, etc., which is defined via optimal isometric embeddings. I'm going to talk about only about very few such notions. So here's the oldest one I'm aware of, and it was defined by Regge and Teitelboim in '74 with corrections later introduced by Baig and Umehu in '87. And they are built on the same philosophy as the ADM quantities, Hamiltonian analysis at infinity, but they do this for the center of mass, and they reach a definition that I'm going to call the BORT, Baig, Umehu, Regge, Teitelboim center of mass, which I'm not going to show you the formula because it's very lengthy, but it's a surface integral at infinity involving Pij and Gij partial k, and no second fundamental form. Okay, now one could argue that maybe k decays so fast that it shouldn't make an appearance after all, and we'll get back to that later. So it does not involve k, and it's known, and not hard to see, that it doesn't always converge. For AE initial data sets. Okay, and one example is to choose G as the Riemannian Schwarzschild metric. And with respect to some coordinates x, so x are now the Cartesian coordinates corresponding to the spherical polars used in writing this metric down. And then y, as before, defined via this sine ln s term implicitly. And if you compute the Baig-Umehu-Regge Teitelboim expression, and then on some finite surface, and then take the surface to infinity, then you will see that it diverges. Okay, that's one example. And so you can ask yourself, so okay, now what? Should we now go back to the definitions of particular coordinates and in here and somehow ask for stronger decay here? Or of course, we should probably put some decay assumption on the mu, but that's not the matter. That causes the problem in Schwarzschild because Schwarzschild is vacuum. So k is 0, mu is 0, j is 0. They satisfy all the decay you would like. So the place where we can fiddle around is we could try to make the exponent here even more negative, and then hope that the convergence problems of the Baig-Umehu-Regge Teitelboim expression for the center of mass go away. The answer is this is not a good idea, because if we try that, then what we have to do is we have to go beyond -1. in the exponent. And if we go beyond -1, then we force the energy, and in this case, also in the case k equals 0, this also means the mass, to vanish. And if it vanishes, not a good idea to talk about center of mass. Okay, so this strategy that was very able to get rid of the discovered by Denisov and Soloviev here does fit for the Regge Teitelboim center of mass. Down, it's not helpful to ask G faster. Okay, so what did Regge and Teitelboim suggest? They suggested to introduce a parity condition that I'm going to talk about later, and that today is called the Regge Teitelboim condition. And that parity condition allows you to look at the surface integral defining the Regge Teitelboim center of mass and treat some parts as even and some parts as odd. And because odd parts cancel automatically in this expression, the surface integrals over round spheres, then you only left with the even parts. And for the even parts, you assume more decay, and then you get convergence. Okay, so you understand this as a Riemannian integration, an indefinite Riemannian integration procedure. But let's not go there yet, and instead look at what Huisken and Yao did in '96. And I'm going to write down the summary of a lot of follow-up work on their paper, most notably by Metzger, by Huang, and by Nerz, each of them in a number of papers. And the collective result is the following theorem. If M3GK is asymptotically Euclidean and has non-vanishing energy, then there exists a unique foliation by constant mean curvature spheres in infinity moreover, provided the weak Regge Teitelboim conditions hold, which I didn't tell you yet what they are, except that they're parity conditions, then the Regge Teitelboim equals the limit of mean curvature going to 0. So here the leaves are going to be denoted like this, over the average integrals sigma to h of the position x. X are the asymptotically Euclidean coordinates here, EA with respect to delta, and this is called the Cmc Center of Mass. And they equal in the following sense: either they both diverge or they both converge to the same thing. So I'll write divergence included. It doesn't say they converge. It says if they converge, they coincide, and if one of them doesn't converge, then the other doesn't either. Finally, if the strong Regge Teitelboim conditions hold, then the big Regge Teitelboim, and hence also the other one, of course, converges. So these Regge Teitelboim conditions tell you that this big Regge Teitelboim definition, which comes from Hamiltonian systems analysis, actually has a very geometric interpretation in the initial data set itself. Namely, it's the average position of a point on a constant mean curvature sphere once you take out these spheres to infinity. And again, I've already shown you that these funny coordinates with the sign ln s bring this Regge Teitelboim center of mass to diverge on Riemannian Schwarzschild. So the same will happen on for the CMC Center of Mass. And I'm lying a little bit to you there because this coordinate transformation does not preserve the weak Regge Teitelboim conditions. And I'll say more about this later. So, but let me first write down these conditions. So I'll pick a parameter eta, which will be 1/2 in the weak and 1 in the strong Regge Teitelboim conditions. And the same epsilon positive and the same chart X as above. And I'll say that the initial data set satisfies the weak or strong Regge Teitelboim conditions in the asymptotically Euclidean chart X if the even part, the odd part of the components of Gij with respect to the coordinates X decay as R minus 1/2 minus epsilon minus eta minus epsilon, and the components of the second fundamental form taking the even part decay like O1 or to the minus 3/2 minus eta minus epsilon, and the odd part of mu and of the components of the momentum density minus 3 minus eta. So if eta was 0, this would be some parity parts of the usual asymptotically Euclideanness condition. And now the eta equals 1/2 tells you that the odd part of the metric, the even part of the second fundamental form, and so on decay by 1/2 faster, and the strong tell you they have to decay by an order 1 faster. Okay. So let's summarize for now. In neither of the definitions of center of mass, neither the Regge Teitelboim nor the Huisken-Yau one via constant mean curvature CMC foliations involve the second fundamental form. There was no integrability condition on the components of mu x or on the scalar curvature or anything like that. And however, we from the definition, for example, of the CMC center, but also if I write it down from the definition of the Regge Teitelboim center of mass, that both these notions transform as you would expect under Euclidean motions. What is tricky and what I claim makes coordinates messy is that the Regge Teitelboim conditions themselves do not transform equivariantly under Euclidean motion. Not equivariant. And rotations are not the problem are translations. Okay. And this is part of a result with Melanie Graf and Metzger, which is work in progress. Okay, so the Regge Teitelboim conditions are not equivariant under translations, and that's making us struggle because we would like the notion of center of mass to be equivariant under translations. Ensure convergence under some Regge Teitelboim conditions, and the conditions themselves are not translation invariant, which is a little bit weird. And so another theorem joined with Melanie Graf and Jan Metzger is what we find is there exist initial data sets with no coordinates satisfying any Regge Teitelboim condition. So I'll briefly word this as with no Regge Teitelboim conditions. Okay. It can easily happen that a given initial data set has a chart in which some Regge Teitelboim conditions, either the weak or the strong ones, are satisfied, and another chart, another coordinate system in which they're not. And I've already shown you this example transforming with the sign LNS, which destroys both the weak and the strong Regge Teitelboim conditions. But we find initial data sets where no coordinate chart satisfies any kind of Regge Teitelboim condition whatsoever. Okay, I'll say something about the proof later if there's time, but let me mention one more thing before going there. In a theorem with Anna Sakovich, we did compensate for this lack of of the second fundamental form K appearing in the definition of both the Regge Teitelboim and the constant mean curvature approach to the center of mass by instead looking at CMC surfaces, looking at something that we call space-time constant mean curvature surfaces. And then the theorem is the same as the one before. There's a unique, for an asymptotically Euclidean initial data set with non-vanishing energy, there's a unique foliation by space-time constant mean curvature foliations, where space-time mean curvature is the length of the codimension 2 mean curvature vector of the surface in the space-time. And there's also of looking at a position vector like this in the set. And if the weak Regge Teitelboim conditions are satisfied, we are able to derive a correction term for the Regge Teitelboim as well. If weak Regge Teitelboim hold, then get K raised correction term. So the modified, and we call this Z. And so then we get this equals the SDCMC in the same sense as before, either both diverge or they both converge to the same thing. It turns out that this definition actually remedies very beautifully the contribution, the lack of contribution of K in the previous definitions, and you can see this, for example, in the fact that it resolves a problem in a graphical example, graphical initial data set in the Schwarzschild spacetime. That I found with Nerz in 15. Okay, so before I say anything about the proof of my new theorem with the Melanie, Graf, and Metzger, let me formulate a conjecture, which will hopefully also serve as a summary of the talk. So the conjecture would be that there is a natural atlas of asymptotically Euclidean coordinates on any given initial data set. AB, initial data set. And the atlas should be such that it's closed under Euclidean motion other than the Regge Teitelboim condition. That in all charts from the atlas, the STCMC Center of the average position of a point on one of these STCMC converges, provided that mu times x is in L1, or maybe if one uses CK methods, that mu is r to the minus 4 minus 2 epsilon. Okay, so this would be the conjecture. Okay, so we say about the so there exist vacuum initial data sets with no Regge Teitelboim condition coordinates. So first, you may ask why how can one even show that there are no coordinates which satisfy a certain condition? And the trick there is to go back to what Bartnik did and see that he, in this volume integral divergence theorem argument I showed you above, he uses harmonic coordinates as a way of replacement of the lack of Cartesian coordinates. So they're geometric coordinates satisfying this geometric PDE. And we also use those harmonic coordinates. And we show that if an initial data set has coordinates in which the Regge-Teitelboim conditions are satisfied, the near harmonic coordinates constructed a la Bartnik, using also work by Leek and Parker to get this in a CK sense. In these harmonic coordinates, a reduced Regge-Teitelboim condition will be satisfied with fewer derivatives. And if this is satisfied in one harmonic chart, it will be satisfied in all harmonic coordinate charts. And therefore, studying whether a reduced Regge-Teitelboim condition can hold on a harmonic coordinate chart is enough to rule out the existence of any coordinates in which the Regge-Teitelboim condition will be satisfied. And then it satisfies, it's completely fine to find explicit examples of one harmonic coordinate on one initial data set where the Regge-Teitelboim conditions will be violated. Thank you.
All right, let's thank Carla. Any questions?
Last question. Can you scroll down to the conjecture again for a second?
I can't hear you, unfortunately.
Oh. Sorry, can you scroll down to the conjecture again?
Yes. Hi, Dan.
Hi. Yeah, so I get. So when you say this is a non-empty atlas, I assume, right?
Yeah.
Yeah. So is the upshot of this conjecture that every asymptotically Euclidean chart you want to have like some definition for Poincare charges? Is that the idea? Or?
Right. Yes. And the issue is this funny way of changing coordinates on Schwarzschild that you can of course do on any initial data set that messes it up. So you have to make sure that your atlas is big enough to contain all Euclidean, one chart and then all Euclidean motions of that chart, but not so big that it includes this implicitly defined coordinate charts to these funny coordinates y. Yeah. Even for just the center of mass. And harmonic coordinates don't do the trick.
Okay. And what's the ST-CMC foliation?
What's the ST-CMC foliation? So if you have a two surface in an initial data set, and you have the space-time here surrounding it, then you can think of the codimension 2 mean curvature vector of this two surface in the 4-dimensional space-time. And you can look at the length. So this is the Lorentzian metric H, right? And this is the space-time mean curvature. And this is what's supposed to be constant. If you compute this, what you find is that this is the same thing as the Riemannian mean curvature. So the codimension 1 mean curvature minus trace over the surface of K squared. So you can compute it from the initial data alone. Okay, so in case K is 0, it coincides with the CMC foliation, and if K is non-zero, it takes some amount of K into covariant, space-time covariant way.
And is the idea in this conjectured atlas, you'd also want angular momentum to be defined there? Or?
Possibly, if you find a similar nice definition for angular momentum, and of course you would have to add a J here in this decay assumption. So I hope that that's eventually what we're going to be able to do also, angular momentum, yeah? And of course, you would hope then that once you have this in the initial data set, you have a way of going to the space-time and look at smooth one parameter families of initial data sets within the space-time so that you can do evolution and boosts. And then have a criterion under on the lapse and the shift of these one parameter families to actually get space-time equivariance under the Poincare group of the notions, or of the correct combinations of the notions, just as the energy momentum force vector does, yeah? And we already know that if it converges, the Cmc Center of Mass evolves and boosts as it should, as you would expect from special relativity, so equivariantly under the Poincare group. In the absence of angular momentum, and once we have a good definition of angular momentum, or a good way of looking at the ADM definition of angular momentum, then the conjecture would grow to include angular momentum.
Thank you.
Thanks.
There is a question by Christina.
Hi, Carla, it's Christina. Nice talk. I just wanted to, you mentioned that harmonic coordinates, of course, don't suffice to complete your conjecture. And let me just clarify, just to be sure I understand. The reason the harmonic coordinates don't satisfy is because they're not closed under Euclidean motions, right?
They are. So if one coordinate chart is harmonic, then of course, if you rotate and translate it, it will still be harmonic.
Okay, sorry. Of course, yes.
Yeah.
So,
Of course.
so,
Yeah,
so
and they're more rich than this, right? You could have terms like one on top of that. So that they are more rich than just the transformations between two sets of Bartnik harmonic coordinates on the exterior of a ball are more rich than just transforming between each other by Euclidean motions.
So can you explain more about why the harmonic coordinates?
Let me try. The bottom line is that they don't have any impact on K. And K, the second fundamental form of the initial data set, appears in the space-time mean curvature, right? Here.
Mm-hmm.
Yeah.
Okay. So you need something that.
So the harmonic coordinates are extremely good at capturing the essence of what's going on in the G.
Yes.
But they're not good at all because they don't know about K other than through the constraint equations. Or in other words, through the decay assumptions on mu and J. And that doesn't appear to be enough. Does that answer your question?
Yeah. Thank you.
Sure.
All right, well, let's thank Carla again.